Welcome to this video. We're going to be talking about proof by contradiction. This is aligned with Mathematics Analysis and Approaches Standard 1.15. In mathematics, we say a conditional statement is a statement that contains if-then, such that the latter, the then part, depends on the former, the if part. So here's an example. If it's raining, then it's cloudy. So the fact that it's cloudy depends on it being raining. And we can write this in logical notation as P arrow Q, or P implies Q, where P is that it's raining and Q is the idea that it's cloudy. So P implies Q. The contrapositive of the conditional statement is where you flip the order and you change them, you negate both P and Q. So it'd be the negation of Q implies the negation of P. And this is actually logically equivalent to the original statement. So here it is. If it is not cloudy, then it is not raining. So this statement and this statement are actually logically equivalent. So sometimes it can be difficult to prove a statement via direct proof. So we use the fact that contrapositive is logically equivalent as a sort of roundabout way to prove the same statement. So we assume the opposite of the statement is true, then show that this leads to a logical contradiction, implying that the original statement must have been true. So let's see an example. Here's a theorem. There are infinitely many prime numbers, and we're going to use proof by contradiction to prove it's true. So the first step in proof by contradiction is to assume the opposite. So suppose the opposite is true, and there are actually a finite number of primes. If that would be true, then we can list them out. P1, P2, P3, so on and so on, Pn, where these are all the primes that exist. But consider the number P1 times P2 times P3 times Pn, meaning you multiply all those primes, plus 1. What about this number? Well, it's not going to be divisible by any of the primes, so if it's not divisible by any primes, it must be prime itself. Yet we just assumed that our list of primes was complete. So there's a contradiction. And now we can say, by contradiction, we must assume that all prime numbers cannot be put on a list. In other words, there's an infinite number of primes. So that was an example of using proof by contradiction to prove there are infinitely many prime numbers. On a similar note, we can also disprove statements by presenting a counterexample. So consider a statement below. X squared plus 1 is prime for all positive integers. So we just need to provide one example of when this is not true. So if we put in 2, we get x squared plus 1 equals 2 squared plus 1 equals 5. That's prime, so that didn't work. Let's try x equals 3. Well, that would be 3 squared plus 1 equals 9 plus 1 is 10, which is not prime. So that has disproved the original statement by our counterexample, x equals 3. Let's try a practice example. Prove by contradiction that if n squared is even, then n is also even. So we're going to start by assuming the opposite of the end. So the opposite of n is even. Well, that would mean that n would be odd. So in other words, n is equal to 2k plus 1, where k is an integer. So let's square that and see what happens. N squared is going to equal 2k plus 1 squared, which is equivalent to 4k squared plus 4k plus 1. Now we can rewrite this as 2 times 2k squared plus 2k plus 1. Now notice that this is just an integer, so I could really rewrite this as 2 times k2 plus 1, where k2 is equivalent to 2k squared plus 2k. Well, notice that this is of the form of an odd integer, which means n squared is odd. So we prove that if n is odd, n squared is odd, which means that the opposite is true. Therefore, n squared even implies n is even. Okay, let's talk about this one. This is a very famous proof that the square root of 2 is irrational, and you need to know it because you're going to see it at some point. And the process is the same, but here's how it goes. So we're going to prove by contradiction that square root of 2 is irrational. So irrational means you can't write it as a fraction where it's an integer over an integer. So we're going to assume that you can, because we're assuming the opposite. So we're going to assume that the square root of 2 is equal to p over q, where p is an integer and q is also an integer. So if that is true, then 2 equals p squared over q squared, which would imply that 2q squared equals p squared. So notice that this is of the form 2k, or 2 times some integer, which means that p squared is even. And by the previous one, we just showed that that implies that p is also even. So if p is even, we can write it in the form p equals 2k. And now we're going to go back to this equation over here and show that q is actually also even. So this becomes 2 equals, p can be now written as 2k squared over q squared. So this implies that 2q squared equals 4k squared. Divide by 2 on both sides, and you see that q squared equals 2k squared. So same thing here. This is of the form 2 times some integer, which implies that q squared is even, which also means that q is even. So if p and q are both even, then they would divide from each other. Two even numbers would divide, which means that this original thing was not the reduced simplified fraction. In other words, this is not possible. So that's how the proof goes. You show that p squared is even, which implies p is even, write p equals 2k, and then show that that implies that q squared is even and q is even, and you show that it's impossible to write it as a fraction. Let's try this one. Show that there is no real number such that 1 over x minus 2 equals 1 minus x. So we're going to start by assuming the opposite, or assume that there is a real number, and we'll let that number be x, and we're going to show that it arrives at a contradiction. So first I'm going to multiply by x minus 2 on both sides of this equation, and I get 1 equals 1 minus x times x minus 2. So that's going to be 1 equals x minus 2 minus x squared plus 2x, which equals negative x squared plus 3x minus 2. Rearranging this a bit, you actually get x squared minus 3x plus 3 equals 0. So remember that this is a quadratic, and in the quadratic formula you have negative b plus or minus the square root of b squared minus 4ac all over 2a. Now if this part happens to be, it's called the determinant, happens to be less than 0, in other words there's a negative number underneath, that's actually an imaginary, which is not a real number. So we just need to show that b squared minus 4ac happens to be less than 0. So here my a is 1, b is negative 3, and c is positive 3. So b squared minus 4 times a times c is equal to 9 minus 12 equals negative 3, which is less than 0, implying that x is not a real number. X is imaginary or complex. So therefore we've arrived at our contradiction, which means that the original statement was true. There is no such x real number where this holds. All right, and that's it for this lesson. Now go ahead and try some practice on your own.